Okay, this is the review video for the homework Unit 6, Module 2C. And we're going to cover shifting, percent ionization, which we've covered, and bases. And buffers. All right, so this is like a typical problem in which you have four options. You're looking at the initial Q, the shift that happens, and the change in pH. So what we're going to do is work through three problems in detail. We're going to use this as a template. Right. So thermodynamic arguments always involve Q. And let's kind of go through the sort of standard standard steps. The first step is your system's at equilibrium, right? That's what we're given. Here it's Ka. And it always starts with, okay, Q equals K. And what does that mean? That means that if we write the products over the reactants using only the aqueous substances, that the equilibrium concentrations are the same as the general concentration, right? So Q is always true. It is the general expression. So even if you add or remove and you're out of equilibrium, Q can represent that. But K will never change. It is the equilibrium concentrations. All right, so there's a change, right? What's the change? We are going to add something, we're going to remove something. Usually if it's removal, it's water. If we're adding, it could be water, could be a reactant, could be a product. So these additions change Q, but do not change K. Okay, so the first thing we're going to do, the first problem is, we're going to do three of them sequentially. And so the first thing we're going to do is we're going to add HCl. And you want to recognize HCl as a strong acid. If we add a strong acid, that means we're adding H3O+. Remember, we add it to the system. The system's all in the same beaker. It's not like we're adding to the left or adding to the right. We add it to the system. When we add it to the system, we want to recognize that H3O+ is a product, and so it's going to immediately increase the concentration of the products. That immediately increases Q because Q is directly proportional to products since products are in the numerator of Q. It's the only concentration that instantly changes. K does not change. So when we look at the pattern here, we look at which of these graphs could represent the addition of a product, only 2 and 3 coincide with that. We have to have an immediate increase of Q. That's what 2 and 3 are showing. So adding product means Q will immediately increase. Now, because Q went up, the shift must be in the opposite direction. The shift is going to be the transfer of material to the other side of the reaction to lower Q to reestablish equilibrium. So to lower the Q, we have to shift material from the products that just went up to the reactants. And that's what we're seeing here. So initially Q goes up, and then Q's got to go down. If Q goes, so in the shift to the reactants, that means the reactant concentration has to go up. And the other product concentration, HCO- must go down. It must be consumed by the reaction of taking products and moving it over to the reactants. And in this case, H3O+ increases, even though we shifted away from it. Remember, the shift is never, is always an order of magnitude lower than the initial addition. So we added a strong acid, the system must become more acidic. Oops. And so in that case, pH went down, and if it does go down, then the answer is 3 for the addition of a strong acid to Ka. All right, let's look at a similar problem. And now in this case, what we're going to do is we're going to add water. Right, so Q, as we talked about in class, Q is directly proportional to concentration. So if we add water, all concentrations go down, so Q goes down. That gives us options 1 and 4 with the addition of water. But to construct the complete argument, we would say, right, Q equals K, right, just like we did before, products over reactants. When you're constructing a thermodynamic argument, this is really the first line that we want to see. I want you to say, first, your system's at equilibrium. Now, what happens? You added a bunch of water, so Q has to change. All concentrations go down. Right, so HCO minus goes down, H3O plus goes down, HCOOH goes down. And now this is much lower than the equilibrium value, than its initial value, which was K equals Q, the equilibrium values. And so what we're going to get is, since Q is low, we're going to get a shift to have to increase to reestablish equilibrium. So Q must increase to match K. And in doing so, by shifting, we have to move material to the products. Right? We need more numerator. The numerator are products. And so that's what we see here, a shift up, make more products. So that's 1 and 4. It's consistent in both of them. And all concentrations independent of the shift decrease because we just diluted everything. But what we see is the amount of moles of products have to go up. And the role of water in Ka is that it is a base, and so pH must increase. So we diluted an acid, it's got to become less acidic, more basic. And we're just looking at the roles of Ka, just to confirm that. These would be the roles of each of the substances. So HCOOH is an acid, water is functioning as a base, its conjugate acid is in the product H3O+. Okay, now let's look at adding a product. No, adding a reactant. So we did the product first. Okay, so adding a reactant. So again, same steps, Q equals K. You know, it sounds redundant if you've watched the other two problems, but it really is the first step. We say we're at equilibrium, and now by adding a reactant, we have now changed it, right? So by adding reactant, Q has decreased because the HCOOH is a reactant, and it's in the denominator. So that means Q went down, giving us options 1 and 4. Right, so so we went down relative to K because K didn't change. And so that gives us 1 and 4 again. We have to shift to products. We always shift away from what we added. So if you add a reactant, you shift to products. More products mean more HCO minus, more H3O plus. Okay, so by doing so, that's how we reestablish equilibrium. So the reactants, so in the shift, the reactants went down. So initially it went up because we added it, but then we shift and it goes down. But as we said in class, this is never, right? This is, the shift is always never larger than the initial increase. So overall, we added more HCOH. The overall concentration of HCOOH goes up. But in the shift, there is a small decrease and an increase in the products. All right, so pH goes down. HCOH is an acid, so the pH must become more acidic, and if it becomes more acidic, the answer will be 4. So these are the key additions that you want to make sure you have a concrete argument and you feel comfortable with it. Adding a product to an equilibrium, adding water to an equilibrium, and adding a reactant to an equilibrium. So in these last 3 problems, we did one example of each using the thermodynamic argument. Okay, Okay, this problem comes from the homework. We get asked this question a lot. So it's very similar to the one we just did, but it's a bit more specific about all the things that are happening. So since we're adding water, water's a base, the pH has to go up. Right, so we know, so this is the argument we just made about water. So the story is Q equals K, step 1. Step 2, you just made all concentrations go down by adding water. So Q goes down since Q is proportional to concentrations. Shift to products. And then by shifting, you reestablish equilibrium. So that's our story. And then we say, well, how do we integrate that into one of these answers? Well, since we added a base, pH has to go up, right? So that already gives us A and D, right? pH went up, you added a base. Water is functioning as a base here. Next, H3O plus goes down because of dilution. So if you add water, H3O, all the concentrations have to go down, so that automatically gives us A. But then, how does the net moles of hydronium go up? Well, the net moles of hydronium go up from the shift, because since Q goes down, we have to shift to products. H3O plus is a product. We're making more moles of H3O plus, and by doing that, we have to shifting to products bring up the moles of hydronium. So that gives us A. pH goes up because we added a base. That's how water's acting. H3O plus goes down because we're diluting H3O plus, diluting all the concentrations, and H3O plus goes up because of the shift. Okay, next question. So we talked about this in class. Here is only showing the A minus, right? A minus, but we could imagine that we could draw the, draw the corresponding, and we'll try to do it. It's going to be terrible, but right, we could draw the corresponding HA version. So this would be HA, and but this is the A minus, right, the base part. And the question is, what is the pKb? Estimate the pKb. Right, so we draw a line, we down there, and what we've said is at the 50-50 mark, when this ratio is 1, because you have the same amount of HA and A minus, right, the 50-50 mark, then what we have is 10 to the 0, and you say, what does that mean? That means 10. So that's 1. 1 is 10 to the 0, and this expression of HA over A minus is equal to pKa minus pH. So what we made the claim is that when we're at the 50-50 mark, pH equals pKa. It's a really important result. It's going to help us pick buffers. This is the buffer zone. And when we look at a graph like this, all we have to do is search for the 50-50 mark, drop a line down. If it's pH, we know exactly what pKa is. So pKa here is 10.2 about. But the question asks for pKb. So we use the relationship of pKa plus pKb equals 14. And we can solve for pKb. 14 minus 10.2 or 3.8. So all of these graphs are very similar in that way that you can calculate pKb from the pKa and correspondingly pKb from the 50-50 mark. All right, so this is a question very similar like we did in class. We're given two values, a pKa and a pKb. And we want to know in our blood, which is at pH 7.4, under that pH, what would be the most abundant species? Okay, so what we're going to do is we're going to first identify the pKa group, the groups. So the carboxylic group that's there, the pK is 1.7. The amine group here has a pKb of 4.2, but since our analysis is centered on pKa, what we're going to do is we're going to convert our amine, our NH2, to the pKa version of it, which is NH3+. This is the acidic, the conjugate acid version of NH2. And we calculate its pKa, and we get 14 minus 4.2, or 9.8. Now that's going to really help us analyze the data, because we're going to see, all right, the pH at 7.4 is more basic than the carboxylic pKa, but more acidic than the amines pKa. All right, so let's take a look at what does that mean. What we're saying is we could draw a dashed line under the pKa. If you're above it, you're in the basic form of your group, right? And that would be for carboxylic acids, that's COO minus. For NH, it's the basic form is the neutral nitrogen. If you're below, if your pH is below pKa, you're in the acid form, and in that case, that's the positively charged nitrogen or the neutral COOH. So that's really what this analysis is about. And so we can create a number line for the acid form. So the number line looks like this. We put our first pKa of 1.7 here. Draw another line, pKa equals 9.8. Now it's just going to help us organize our groups. So first of all, any pH less than pKa is definitely going to be in an acid form. So that means the pH below 1.7 will be in both acid forms. Once we cross over, if the pH, remember this is a pH line, pH is going this way. So when pH is below 1.7, acid form. When the pH is greater than 1.7, then what happens is we now have the base form as the highest abundant species. Now NH3 plus is going to remain in its acid form until we pass in pH the pKa. Then it will change to its base form, right? So this is what this group looks a lot like that group, right? The base form, both of these are in the base form at any pH greater than 9.8. But at pH 7.4, we're sort of in the middle, we're between it. So we're in the base form of the carboxylic group, but the acid form of the amine. And one thing to keep in mind we also like to keep track of the solvent here. So any pH less than 7, hydronium is in higher concentration. That's what it means by acidic solution. Any pH greater than 7, hydroxide ion is in higher concentration. All right, so in this question, we now have all the information we need. So at 7.4, we expect the carboxylic group to be in its negatively charged base state. At pH 7.4, we expect the mean to be in its positively charged acid state, and that would give us answer C. Okay, and we can see some other answers kind of appear. B is the case when pH is less than 1.7. Right, that's in the neutral carboxylic group, but a charged nitrogen. And then, let's see, option A is pH greater than 9.8, right? Greater than 9.8 because that is the negatively charged oxygen in a neutral nitrogen state. So in this state, it doesn't happen. Right, so we have another question that's often asked. The same issue. We're given pKb for a nitrogen group and a pKa of an OH group. So what is the acid form? What is the base form? And how do we put it in the analysis, that structure of analysis that we did earlier? And then identify which substance is going to be in the highest abundance at different pHs. Right, so let's take a look at, first get the pKa, so the pKa is 10.2, and now the pKa, so where an acid analysis is based on the acid form, we have to put NH3 plus, which is 14 minus 8.7, or 5.3. Okay, so let's put our table together. Okay, so we're creating the line here for pH for the two acid groups and the pH and the two pKa's. So one pK is 5.3, and maybe we could write that a little bit better. So 5.3, and once the pH, remember this is the pH scale here, once the pH is below 5.3, then we're in both acid forms. If the pH is between 5.3 and 10.2, then the base form of the pK equals 5, which is the nitrogen group, will take on its base form. But the oxygen, the OH group, does not change until you cross its pKa. All right, so it looks like that. So let's go through all the possible options here. So option A is going to be the case in which any pH below 5. So D is going to be the pH between, let's see, this is neutral nitrogen and OH. So C is, okay, yeah, so this is going to be any pH, so 5.3 less than pH less than 10.2. That's going to be option D, right? So any range in there is going to have a neutral nitrogen and OH. Option C is going to be pH that is greater than 10.2, right? So any pH greater than 10 is going to be option C. And then option B cannot be made. You can't have a positively charged nitrogen and a negatively charged oxygen in this model, because the negative charged oxygen occurs at any pH greater than 10, but by then the nitrogen is in its neutral state. And so for pH equals 2, the answer will be A. Right, so the next couple slides are dealing with buffers. So we want to know what is the best buffer, like what is the best system here to be able to find a buffer that has the maximum capacity of pH equals 8. Right, so maximum buffer means we have 50% of a weak acid and 50% of a weak base. They have to be both in equal concentrations to have the maximum effect, meaning they will accept both strong acids and strong bases. That's what we call maximum buffer. But if it is 50% weak acid and 50% weak base, under those conditions, pH equals pKa. So what we're really looking for is which one of these systems has a pKa of 8 or a Ka of 10 to the minus 8. And when we look at these systems, we see that ClO minus HClO has this behavior. Now, is it exactly 8? And that's... So it doesn't have a pH of exactly 8, no, but it is very close, right? If we look at the other substances, then the pKa is around 4, 10. So these would not be good choices, but here the pKa is equal to 8. Now, but what is pKa? So we look at pKa here. pKa is minus log of 3.2 times 10 to the minus 8, and this is 7.5. So it's not exactly 8, and you say, okay, well, it's probably the best buffer, but what would be the exact recipe to create a pH equals 8. And under this condition, this is where the Henderson-Hasselbalch equation is very useful. So let's take a look at its two forms. So what we have is pKa equals pH minus log of the concentration of A minus over HA. And we really use this formula when given pKa and given the ratio, you know the ratio already, you can calculate pH readily by saying pH is equal to pKa plus log of A minus over HA. So this is the Henderson-Hasselbalch version where you know this, and you want pH. But as we saw in class, this is not always what we're after. Sometimes what you're asked to do is calculate the A minus over HA. Like, what is that ratio? And in that ratio, we would want to use the form of 10 to the pH minus pKa. And so, and we use that when given pH and given pKa, which is the case we have for this problem. We have this problem where we know pH is 8, so A minus over HA is equal to 10 to the 8 minus 7.5, or 10 to the 0.5, or 3.1. So what we would want to have is 3.1 times A minus for every 1 HA. And if we did that, if we had, let's say, for example, 3 molar A minus and 1 molar HA, if that would be a recipe in which to make a pH equal 8 for, and when we say ClO minus, what we really mean here is 3.1 molar ClO minus and 1 molar HClO. So if we did that, that recipe will give us pH equal 8. So that's often asked for, but this is the key to understanding when do I use Henderson-Hasselbalch. Well, you use it when you're given the ratios and pKa, and you're asked to calculate pH. When do I use the other form that we used in class, and that's given pH and pKa, and you're asked to find the ratio. Okay, so we have a problem that's similar to that. If one adds 0.1 molar of the weak acid HF to a solution with a pKa of 3.2 to a solution with a pH equals 7, which species will be in most abundant, right? Which species will be most abundant, and we want to quantify it. All right, so here we're starting with from Ka. Right, well, first we're going to write the equation just to make sure it's clear. We're under Ka here. And if we write Ka, it looks like this. And if we take the minus log of both sides and do some, math work, we can develop the Henderson-Hasselbalch equation. Now, a lot of us are just going to start with this equation, so it's not so important like you derive it each time, but it kind of shows you where it's coming from. We're just looking at Ka. And so in this problem, we're given pKa and pH. So we put everything on the side that we know. So pKa minus pH is this minus log F minus over HF. Now, as we mentioned in the last problem, this is not a very convenient way to solve for F minus, ratio of F minus to HF. What we can do is to take 10 to both sides, and then we get this expression. So this expression is useful. We know pH minus pK. What it says is if pH is greater pKa, then we have F minus concentration is greater than HF. Right? So that's what that equation is telling us. So we put the numbers in, and we see that's 10 to the 7 minus 3.2 is 10 to the 3.8. And so we get 6,310. So much more F minus than we do have for HF. So it's a very convenient way. So remember, try to be flexible here. If you're given pH and pKa, you're going to want to use this version of the problem. If you're given the ratio and pKa, then you would use this one to find pH. Like this problem. Okay, so here we're given different amounts. So we're just going to start with the Henderson-Hasselbalch equation. And now we're given pKa. Well, we're given Ka, which we have to use to find pKa. We don't know pH, but we do know the concentrations now. So now this is ideal for using the Henderson-Hasselbalch equation. We want to solve for pH. All right, so solving for pH, if we take the minus log of 1.8 times 10 to the minus 5, we get 4.74. If we bring over the plus log 0.2 divided by 0.3, the answer is 4.74 minus 0.18, and the pH is 4.56. And then we ask, does this make sense? If we have 0.3 moles of the acid, but only 0.2 moles of its conjugate base, so we're on the acid side, meaning if we make our pH line here, so the acid form, highest concentration, base form, highest concentration. Does it make sense? If we have more acid, 4.5, 4.7, and it says yes, we should have more of the acid form. We do in this problem, it's 0.3 over 0.2. And so yes, this does make sense. Okay, so the final question on the video is a problem that lots of students asked about in Discord, so I thought I would bring it up here. So we have phenol, and we're given pKa, so we're going to make our table. pH equals pKa, acid form to the left, base form to the right. And the key in this problem is to know, one, what is the acid form of phenol, what's the base form, and two, the solvent water. In the solvent water, what has the highest concentration? Now, for doing that for water, we have to draw a line at pH equals 7. Okay, so all acid forms to the left. Okay, now we're not going to, so the acid form of phenol is C6H5OH. It's an oxygen-containing molecule. Its acid form is neutral. Now, when we think about its base form is going to be highest in concentration and will have a negative charge. For the solvent water, H3O plus is the highest in concentration at any pH. For any pH, less than 7, and if pH is greater than 7, it's hydroxide ion. Okay, so we can kind of see now if the pH equals 8, right, we have to be under the acidic form of phenol because we're at a pH less than pKa. And then at pH equals 8, we definitely cannot be under hydroxide. So if we look at answer A is never possible. We never can have the negative charge in an acidic solution, right? So this is acidic, basic, right? So that's what it's saying by the pH. pH equals 8 is telling us, are we acidic or are we basic? So any pH greater than 7 has to be basic, so that gives us answer C and D. And now we're just looking at where is 8. So pH equals 8 is right here. And under that case, under C3OH, we have a basic solution, so the answer will be D. All right, so we can't pick C because that would only be true at any pH greater than 10. If the pH is between 7 and 10, the answer is D. And the answer is B for any pH less than 7. Right, that concludes this review video for Unit 6, Module 2, C.